So, here's the thing. That first example was just kind of a general idea. Now let's get into the nuts and bolts. What the shit to do when they give you all this information. You gotta give everything they tell you and everything they ask you symbols. Because then when you set things up, you know exactly where to plug whatever. So what would the symbols be for that number? No. So if I pump air into a spherical balloon, what is changing as more air goes in? The volume is changing. If just the area is changing, that'd be really weird looking. Kind of have like a Jupiter in my, like it has a ring coming out from it. It's got a center ball. It's like, no. Okay. So dV dt is 100. All right. We'll put this right now. dV centers. How do I write the question in symbols? Not too bad, right? How do I write the question in symbols? How fast is the radius increasing? So what does that relate to? That's d what? dr dt. Don't make too big of a deal. So how fast is the radius changing? dr dt. That's the question. And the last thing is, diameter is 50 centimeters. Now diameter is dumb. I could rewrite every formula we know in terms of diameter, but we have it in terms of radius already, so why mess with that? So I'd rather say r equals 25. Cool. So I've summarized what they told me in symbols that will show up in my work. That makes sense. So where's the starting point, though? What is the thing that I'm actually working with? The what? The volume. What's the volume of this spherical balloon? What's the formula for it? Beautiful. 4/3 pi r cubed. I can't remember if it's, whenever you get a math book, you should look at the front cover, the back cover, see what the hell it tells you. I think it tells you area and volume formulas in there. Can't remember. You good? Yeah. That's the wait and see approach. Maybe. She'll answer her own question. All right. Now I've got the initial function for what it is I'm talking about. Now I take derivatives. You guys do that. Take the derivative real quick of both sides. With respect to, of course, t. So now we're going to take this known thing and create a function that relates the rates of change. Just by taking the derivative of both sides. Let's see if they tell you. There it is. All right, what do you guys get? I'll do this side. Whew. What do you get on this side? Yeah, the 3 would come down making this 4 pi r squared dr dt. What do you think 4 pi r squared is? Surface area of a sphere. Holy shit. Remember, that's the same thing as what we were doing earlier with a circle. Oh, that's too flippin' awesome. Shit. So it's just like putting a thin layer of tape over the entire surface of a balloon because you got nothing going on. But that's what would happen. It would change by that. So now, do I know everything I need to know to figure out what I want to know? So I don't know this. That's what I want to know. I need to know that. I do. I need to know that. I do. Kick ass. So that's why that step is so stupid important. Identify what they tell you and what they ask you so you can find them in your equation. If you forgot to do this, and you have that sitting there, you're like, okay, that doesn't make sense. Oh, I forgot to do that. Oh, shit. Well, there it is. So now just plug stuff in. 100 equals 4 pi 25 squared. And now it's just all about, what's 4 times 25? 100. So that cancels with that. Divide by 25, divide by pi. There it is. That's the exact answer. Sickle, and then whatever the hell that is when you plug it in your calculator.
Plug it in your calculator.
So what do you get when you plug it in your calculator? Just out of curiosity.
1, 2, 5.
Say again, sir?
1, 2, 5, 6, 6,
0.125?
1, 2, 5, yeah.
6, okay, 126. Who to what? What would the units be here? What would the units? Beautiful. Centimeters, because I'm talking about radius. That's a length, not a. Don't put cube just because they did. They put cube because it's volume. Think for a second about the units and what it's talking about. All right. All right. Last thing, and then I'll let us out of here early because we had a quiz. You're all like brain fried. I understand. Yes.
Ask for delimitation.
Say again, sorry.
What is the delimitation?
Why does it show up? Because I got to do the same thing to both sides. So if I take the derivative of this with respect to t, I better take the derivative of this side with respect to t.
Oh, okay.
Yeah.
And it's the derivative of that variable is
Yes.
it's not
So.
dRdt.
Oh, yeah. So I'm doing. What am I doing to both sides to go from here to here? I'm doing d by dt to both
I
sides.
thought it was dr by dt.
But in the process, I do get that because of the chain rule.
But not on the
Yeah, not on this side, is it? Because it wasn't just a v sitting there. Okay. All right. Let's see if you guys can handle what I'm about to say. So, what do we figure out? The radius is changing by 0.128 centimeters per second. So, help me out. What was the radius to begin with? Gather. The initial radius is 25 centimeters. So what was the initial volume of this thing? No, that's how much it's changing. It's the rate of that. If the initial radius was 25, the initial volume was 4/3 pi 25 cubed, right? Okay, so what would that be? It's like 622. How close am I? Probably way off. That's what I get for trying. Oh, 300 times. Wait, 300 times. Oh, what is it?
65,000.
Okay. I left off a couple of things. 65,000?
65,449.
65,449? 0.8? Blah, blah, blah? Okay. All right, now. Stay with me. You ready? So you guys can do this. If I add 100 cubic centimeters to that, how much time has gone by? Oh, I love that question so much. You're like, what? If my name is Fred, how blue is my dog? What? No. If I add 100 cubic centimeters to this, how much time have I let go by? 1 second, because it's changing by numbers per second. So in your calculator, just put plus 100. All right, let me do this with you. Remember, this is the last thing we're doing. We're almost done. Okay? I know I'm weird. Oh well. Yeah, okay. So if you add 100 to that, that would be the volume after a second. Now if I solve for the radius now. So whatever you got for the volume, let's do 3/4 times it divided by pi cube rooted, right? Solve for the radius. Oh, I lost the volume, but oh well. So I saw what the volume was. I let it change by this much, which means 1 second has gone by. If I now solve for the radius, I can see if the radius is changed by about what I predicted it should change. After 1 second, the radius should have changed by this much. Let's see if it did, or this shit is stupid. Right? Some of you guys think it's stupid already, but it's going to be true. Let's see. So is everybody decent with it? I'm just solving for r here. If I take what I just got times 3/4, right? Times 3/4 divided by pi, get that, and then take a cube root of that. I get 25 point, where'd it go? Oh crap. 0.128. Is this supposed to be 0.0128? Ah, that makes me feel a little better. So how much did the radius, what was the radius at first? 25 centimeters. What is it now? 25.0128 centimeters. So how much did it change by? 0.0218 centimeters, which is what we predicted it would change by. I like doing this. It's a concrete example of what the shit we just did. This is a prediction. Now, does the radius change at a constant rate? What do you think? That's kind of an evil question, but no, it won't. Because it's a cube relationship, right? So the minute, if I let a minute go by, my prediction will be off. Because it's a straight line. This is saying it keeps changing, but I know it's not a straight line. So I'm going to be off the further I get away from my initial time. So if I let 60 seconds go by, I'm going to be way off in my prediction. That's because this is only true at that instant. Okay. All right. I think that's enough. So next time I'll have this little handout we'll work on that's example problems from related rates. And then we might get through, I might not try to push it too much. You might get through one more section. I might put one section on the next test. We'll see on Thursday. Because we got that quiz first thing Thursday. Okay.
No.